so we see that up to 20% they are not unvanished. But the thing is that this calculation get a pretty good result below 10%. So here get more and more fluctuation. So it's possible that if we can go to further D, like in future, probably go to 20 or 30, then it dies around 10%. Then we have a kind of result consistent with magnetization calculation. And also, so from DMRG we can also, and also from tensor network, actually we can extract this so-called condensation energy. So here I assume that the normal state actually is a Nagorka state. Assume we apply very strong magnetic field to polarize the system, then it's a Nagorka state. But then if the Zeeman field is not big enough, it go to some new p+ip superconducting state, and there's energy difference. So this energy difference is almost linear in doping. And I can briefly fit this condensation energy, and also this p+ip superconducting order parameter. So they are almost proportional to this doping. And if you look at this phase shift, actually, so here I have delta triplet. Yeah, I think this x, y, z just means the triplet have 3 components. They all have share the same shift. Okay. So we try to understand what's the mechanism behind it, because this Emergence result looks like a pretty strange and abnormal, because it's very close to the Nagorka state, but it is not. So first we want to examine that what happens if we put a very small j, or in other words, we put the u not infinitely large but finite. We still perform the ground energy calculation on about 1,000 sites. So in the imaginary time evolution, the ansatz is for infinite system, just like a variational quantum in the color. But if we want to extract this correlation function or ground energy, we almost put on small size. But not so small, almost 1,000 sites. So we hope it already approached this thermodynamic limit. So for finite U, actually, we even get a better energy accuracy. So the energy accuracy almost 0.2%. So for the infinite U, the error around 0.4%. So if we compare to this DMRG data, we see that for 2 cases, like T over J equal to 30 or T over J equal to 50. Yeah, this is 30, this is 50. We get a pretty good agreement in different dopings. So here I also push this D, the inner dimensional tensor, to 14. So look at this data, we find that all these ground energy much lower than the Nagorka state. And then we measure this polarization. Very surprised, it goes to 0. That just means this infinite U point may be some singular point or not so stable. If we turn on very small j, we can kill it. Okay, then we also measuring this p+ip superconducting order parameter, and by choosing different kind of T over J and a different boundary dimension D. If we go from 10 to 14, we find this is symmetrically suppressed. And if we make some 1 over D kind of scaling to infinite D limit, you can think about this. Actually, the p+ip order parameter also vanish. So that means if we turn on some very small j, or the U is not infinite, it's potential state without any kind of order. No magnetic order, no superconducting order. So it's different from the infinite U result. But from this point of view, it's kind of a little bit sad, because looks like in experiment there's no way to realize the p+ip state, because experiment U always finite. But it's not so bad, because we can actually turn on some Zeeman field. So here I want to mention that for this completely disordered state, I have a conjecture it might be an interesting non-firm liquid. But we are still doing more concrete calculation to see what kind of property of this non-firm liquid could have. But on the other side, for this experimental purpose, actually, because we think about this p+ip state very close to the Nagorka state. So at the beginning, we can think about we apply some Zeeman field. For example, we add some in-plane magnetic field. for polarized state. If the Zeeman field is very, very large, there's no doubt we end up with the Nagata state. But if it's not just an intermediate, just on the order, let's say on the order of the J, or on the order of T square over U, so this is typically can be accessed by any kind of lab. So it's very interesting that there's phase transition if we turn on this Zeeman field. And below that phase transition point, it's definitely similar to this 0 point case. So this p+ip state, all the parameters get suppressed when we increase d. And above that, it's not suppressed anymore if we d go to enough large. And also this magnetization, there's a jump, almost go to fully polarized, almost 100%. But here still it's like 99.5 something. It's not because if it's 100%, you can show it cannot be a superconducting state. It must be a kind of half matter, yes, some defined by Kivers. Okay, so from this point of view, it's still optimistic because in an experimental lab, we can just apply some Zeeman field. Then we can stable this p+ip state and make use it to do some like quantum computation process. But theoretically, we are interested in that the mechanism of such kind of p+ip state. So now I try to go to this field theory description for the.
Sorry.
Okay.
Yeah. So so we go back one.
Yeah. Sure.
Yeah. The phase transition is that first order phase transition or something jumps or?
It looks like here we don't have enough numerical result, but it looks like a second order. If you go to large D, it looks like this jump get more and more smooth. So if you go to D equal to 10, looks like this magnetization have a jump. If you go to D14, it's more smooth. Of course, I need more data, but you actually have two more data here. It looks like much more smooth than the D equal to 10.
So it seems to me that the order parameter just change its size, but nothing will emerge from zero, right?
Yeah. Here because you already add this. Once you already add some magnetic field, it's just like a paramagnetic phase. It's this is not the true order parameter. The order parameter you need to suppress this background. So here I just problem magnetization, right? It's already have a background. Even in this paramagnetic phase, you add some small Zeeman field, it can have a polarization proportional to this Zeeman field.
Yeah, no, I don't understand why you call it phase transition. Since actually seems to be the no symmetry is broken and.
Oh, there is. So here this U1 symmetry broken. So here it's not a superconductor. Here it's a superconductor. Yeah.
Delta is not zero though, right?
Sorry?
Wait, but delta is not zero when h is very small, right? Because it's still.
Oh, but you need to do 1 over D scaling. Yeah, in numerical you can get nothing there if you don't do scaling.
So how about for the smaller ratio? Here T over J is 30.
Right.
If T over J equals 3, we will have a similar feature or
Oh.
calculate.
Then it's D plus ID superconductor.
Oh, it's D plus.
Yeah, actually that's our previous paper, right? So we have this D plus ID.
So when that difference happens, when you have P plus A, when you have D plus.
Yeah. So in the end of the talk, I will mention the global phase diagram. Yeah. So before that, I try to explain this kind of interesting mechanism based on some quantum field theory. So because in the infinite U limit, the state is pretty simple, just kind of fermagnetic order. So we can think about, we can apply this so-called slave particle technique. So we can decompose this electron into some fermionic Coulomb and a bosonic spinon, first proposed by Phil Anderson. We also want to simplify the problem. We're interested in the phase transition in the presence of Zeeman field. So we think about the effective model do not have actual SU2 symmetry, just have a U1 symmetry. So in the U1 symmetry case, this model can be simplified because this spinon part is pretty simple, like B down equals 0 and B up have some order parameter. And this theta actually is phase fluctuation of this U1 order parameter. Then we have some XY model description for this spinon part. But of course, both this Coulomb and spinon, they need to couple to some U1 gauge field. So this Coulomb part in order to make a simple calculation, here we try to choose a relativistic dispersion. So usually people think about if we're starting from 0 doping, typically it's a quadratic dispersion, not relativistic. But we can think about some different limits. If we in the phase diagram, if we starting from this 50% doping. So here basically we have some. So here we have a quadratic band for this holon. But here we can have this relativistic dispersion for the holon. So numerically, actually, we tested that in the presence of Zeeman field, this p+ip stays stable, even kind of approach like 40%. So it's very close to this data limit. So in the field theory, we don't want to starting from the small doping. But in principle, it's possible, but it's just technically hard because if it's non-relativistic, there are some difficulty in the calculation. But so that's why I want to just focus on this region. But if we're interested in physics, like around, let's say, 30%, maybe it's also reasonable to starting from this 50% doping. Then in the 50% doping, it's pretty simple. We just have two-component Dirac fermion. So this A equals 1 or 2 because we have AB sublattice. And this holon also coupled to this fictitious U1 gauge field. But in the Higgs phase, because the fictitious U1 gauge field quantum fluctuation has been suppressed, so we can have some controlled calculation. So, so the idea is the following: that we first just apply this so-called dual vortex representation. So the duration actually is standard, but so how many?
Half an hour.
Oh, okay, yeah. So then I can briefly explain this derivation of this vortex representation. Yeah, basically it's just a trick that instead of using this kind of real phase field, we want to, because we want to study this kind of potential non-perturbative effect, we want to go to this so-called dual representation. So here this phi is a scalar field which represents this U1 vortex. So technically, the idea is that, for example, if you're starting from this XY model, starting from this Higgs phase. Yeah, so I just ignore this coefficient. So starting from here, technically you can just decouple this by apply some Haber-Stranovic transformation. For example, this is just equivalent to this J mu square and plus I J mu and function mu theta minus A mu. Okay, once to such kind of formal decouple, you can integral the theta because now theta is in the linear. We don't want to this kind of study the property of this phase field. So once we integrate theta, we impose some constraint, partial mu J mu equals 0. So then you can solve this J mu by some dual gauge field, epsilon. Yeah, so this is actually very standard derivation in the quantum field theory. So the so-called dual vortex representation. Then we can have this kind of dual gauge field, small a mu, and this dual gauge field can also have some singular configuration. So in the partition function, you need to also sum of all these singular configuration. And actually, this derivation can be found in Nagaka's book. So once you sum over the singular all the singular kind of configuration, you can actually turns out to be equivalent to introduce this Klein-Gordon field. So phi is a complex field, which is coupled with this small a mu, and this m square is basically some so-called vortex core energy. So the core energy input by hand. So once you put back this kind of terms, once you solve this J mu, so the J mu square just this term, it's a Maxwell term. And there's a mixture term, J mu, A mu, so this is a Chern-Simons term. So in this dual representation, we have a pretty simple picture. basically the Higgs phase now kind of described by a kind of topological term, the so-called Chen-Simons phase between this capital A mu and small a mu. And due to the presence of the Chen-Simons term, this capital A mu quantum fluctuation kind of suppressed. And this small a mu, it can have a Maxwell term, kind of immediate logarithmic impressions between vortices. This vortice is pretty simple. It's just kind of coupled to this dual gauge field. So basically we can do some calculation based on such kind of Lagrangian, because in this Lagrangian, this capital A mu just a linear kind of action. So we can integrate this capital A mu, then we can do concrete calculation for this Lagrangian. Okay, so here I also want to mention here we usually put this chemical potential term. So you see this chemical potential term actually violates this Lorentz invariance, because there's a finite kind of Fermi surface. Okay, so now basically for this Lagrangian, we can ask whether there's some potential instability for this Navier state, because it's kind of just equivalent representation, almost equivalent representation of that one. But naively looks like there's no instability, because yeah, in the previous action, you can think about we just have this A mu has been springed, so they're just like on-site repulsing between this side. But this is just a Maxwell term, so it's just also usual Coulomb phase between this phi. So everything is repulsive. There's no attractive impressions. So there's no instability. But it turns out this kind of derivation actually is in the dilute limit. But for the Navier state, we can imagine it's not a dilute vortex limit. The reason is that if the doping is small, actually, if we go to this Navier limit, this vortex is just becomes a single spin flip, which does not cost energy at all. So we can conjecture that at some finite doping, let's say around 20%, maybe the core energy is still very small, and it's very easy to create a lot of vortices. And if we beyond this dilute limit, actually it's possible to add some non-minimal coupling, namely such kind of so-called charge current coupling. So it's non-minimal because usually this J mu just coupled to A mu, so J mu is just the vortex gauge invariant vortex current. But here it's directly coupled to this field strength. So that's a secondary term. And usually if we just think about Dirac cone, this is irrelevant. But in the presence of chemical potential, it's kind of reasonable to conjecture cannot be simply ignored. And if we, as I mentioned, because now A is only have a linear in the action, so we can integrate explicitly. And once we integrate, we get just a very simple physics. Just means this if due, the due of the fictitious small gauge field A mu, the due gauge field, basically the field strength just equal to the fermion current. This is actually also reasonable because for this vortices, this fermion basically just like magnetic flux. Right? So once we integrate a capital A mu, we just get such kind of term. But if we put this inside of here, we find this is nothing, just the Coulomb current. So that's the reason we call it current coupling. So it's just the Coulomb current coupled to this Skermian current. And once we include such kind of non-minimal coupling term, we can do the calculation and integrate everything, and in the end you get something interesting. So in addition to this kind of on-site repulsive term, we get some kind of term evolve this derivative. But this term actually is pretty interesting because this term is still Lorentz invariant, so we can just look at this some particular component. So the component, we just look at this component partial I and psi, gamma 0 psi. So this kind of thing is actually it's fermion density. It's almost just a fermion on-site density. And this p+i, you discretize it. It's almost like Ni minus Nj. And if you square this kind of term, it turns out it's a attractive interaction, because this is just equal to Ni plus Nj. So this is chemical potential, and you have a negative sign here. So you have effectively attractive interactions between this Holon field. But in our previous calculation, we have already shown that this Holon now is a kind of a spinless particle. If they have this effective attractive interaction, it's not surprising it must be a p+ip superconductor. So now we understand this physics we get from the numerical result. Okay, so since there is still some time, I can also provide some alternative explanation, maybe more straightforward or more simple. Because from numerical result, we know that this polarization very close to fully polarized. So we can just assume this downspin density very, very small. So just like delta zero, like almost 1%. Then we can rewrite this Hubbard model in the following way. So it have two components. It have two terms. So the first term is for spin up, and the second term for spin down. Because the electron almost spin up, so it's very close to the Nagorka limit. So for the first term, we can just make some mean field approximation. So it's just almost like upper electron hopping. If that is 0 equal to 0, then it's exactly, we just have the first term. It's a true Nagorka state. But the second term actually interesting. So this term just a projection to the non-double occupancy space, right? If you have some n down here, you cannot create a C up. So this is just from the infinite U effect. So we put some projector here. But for this kind of down electron hopping term, you find that there are some pretty interesting that you can rewrite this term as like Si minus and Ci diagonal. Just like when you create this fermion, you also want to flip spin. And at low energy, you can think about this as this spin degree freedom is some kind of like independent emergent degree freedom. And then this term pretty interesting. When electron hop, it also want to make a spin. So it's like electron hopping and a spin flip interaction. And this term you can further express into two contributions. So the first term is very normal. It's just a kind of electron hopping, but then there's a kind of XY exchange term. If this term dominant, then obviously we will get a ferromagnetic state, kind of Nagorka state. But the second term is pretty interesting. It's kind of, we have this electron current, upper electron current, coupled to this, basically it's a Fermion current, because it's easy to see that this term just Z component of this spin chirality. And if we assume this term have an extremely strong quantum fluctuation, for example, we can phenomenologically add this kind of Gaussian fluctuation for this spin chirality. And if this kappa is very small, this fluctuation, if this kappa large corresponding to the bigger quantum fluctuation, then we can integrate this Gaussian fluctuation, we get this attractive interaction as well. But if this term dominant, we just, it's the ordinary kind of ferromagnetic order. This term dominant, we will have a p+ip superconducting state coexisting with the ferromagnetic order. Okay, so in terms of a single picture, you can just think it in this way. We have in this starting from this Nagorka state, we can have some like a Holon. So in the Nagorka state, this at finite doping, this Holon just form a free fermion surface. But if we assume that when this Holon moving in the system, there's some virtual process to create some skirmion. But the skirmion just like magnetic flux for the Holon. So the Holon will get a kind of doing some cyclotron motion. So at long wavelengths, it's pretty like you couple energy that it scattering to the Holon and change the momentum of this Holon from one Fermi point from the surface to some other momentum K. And because such kind of mechanism, you can mediate a pairing for the Fermi surface and make the on-state. Okay, but it's almost like a BCS theory, but still something novel because it's not usual photon-mediated interaction, and spin charge separation is crucial. And based on this spin charge separation, we can have this fermion well-defined fermion defect, and this fermion defect actually can mediate this kind of interaction. But then it's also easy to conjecture that in certain cases we can think about the fermion can condense. So the fermion condense phase actually, by some simple calculation, you find it's almost like QED3, but with a chemical potential term. So because the presence of chemical potential term, people argue this kind of QED3 might be not suffered by the confinement issue, so might be a very good candidate for non-fermion liquid. So that's still a conjecture. So we don't know whether it is true to describe this U large but not infinite limit or not. Finally, let me just tell you some interesting experimental material. So one kind of material called indium copper vanadium oxide. So the structure of this material, we have some indium oxide layer, like insulating layer, which is not active. So the active layer basically is this copper vanadium oxide. So this copper and vanadium, they have the ratio 2/3 and 1/3. So basically, vanadium occupies the center of the hexagon. That's why they are ratio like 2:1. And the copper forms this hexagon lattice, and it's the active degree freedom. So it's 2 plus spin 1/2, and the vanadium just 5 plus spin 0. Okay, so effectively it's just like a single band Hubbard model, but there's more complications in the true LDA calculation. But naively we can just approximate by one band Hubbard model. And experimental people also see this two-dimensional kind of antiferromagnetic order in the susceptibility measurement. So it's could be very interesting that if we can, but we don't know how large is the U. Maybe U would equal to 30 or something, or maybe 100, but of course it's not infinite because I have feeling people still observe this antiferromagnetic order. So if we can dope this material, maybe there are very interesting things can happen. Actually, yeah, according to our previous calculation, if this U over T not very big, like U over T around 10, if we dope the system, we find it's basically it's a D plus ID topological superconductor. But if in today's talk, I'm talking about if we can add in some Z-man field, maybe drive it to some p+ip topological superconductor. And also recently there are other material like this helium-3, if they can absorb under the substration, and also some organic material, there might be chance for such kind of
so based on the plot, actually, it's like the J will be at least more than 100 Kelvin, right, in the system?
In this case, no. It's kind of, I think they claim the
compare with the QED's behavior, actually, I think the J will be at least 100 Kelvin.
Yeah, I'm not quite sure. They claim this effective J like 30 to 40 Kelvin. Yeah, maybe some detail we can check that later. Yeah.
But in your calculation, the H will be at least be as much as J to drive the two sides.
Yeah. So this material maybe still not the best one. So we need some material with even small J. So but the other material might be possible. So let me just make a conclusion, and yeah, maybe it's time. We kind of just basically apply this Grassmann tensor for that state as some relatively unbiased variational method. Unbiased in the sense compared to variational quantum power to study some strongly correlated system. And interesting thing is that there are some numerical evidence that for the doped infinite Hubbard U model on Honeycomb lattice, it's p+ip superconducting state coexisting with the ferromagnetic order. And we also make some proposal for a non-BCS mechanism for such kind of p+ip superconductor. And there could be also some experimental realization. So yeah, finally I want to answer Shevon's question. So here just one plot for brief phase diagram. Let's say focus on 10% doping. So the phase boundary, we are still doing more calculation for the full Hubbard model. But basically, like around U over T equal to 4, below that, we find it's just a semi-matter. There's no superconductivity at all. And Above that,